Okay, next we're going to talk about structured data. So a user-defined data type is one that's specified by a programmer rather than built into the programming language. So the built-in types we know about are int, float, character, bool. Well, these cannot be broken down into smaller units. We say they are atomic. So what I mean by atomic is that they're not composed of any smaller things. So a string is not atomic, and it's actually not even a built-in type either, because we have to pound include string when we want to use a string. But a string is not atomic because it can be thought of as a collection of individual characters. A string is made up from or composed of the smaller character data type. A structured data type is a data type composed of other data types. Okay? So by definition, a structured piece of data is not atomic. A structured data type allows us to group related data together and give that type a name. So grouping related data together is a form of abstraction. Instead of having to actively think about all of the individual parts, we can group them together and think about the whole as a single unit. This is especially useful when, for example, we want to pass some data into a function. So oftentimes with a function with many parameters, we can make the function call a little bit simpler if we grouped all the related data together and created this structured data type and just passed around a single whole unit to a function. So as a contrived example, it turns out an int is made up of 32 bits. Some of those bits store the number, and some of the bits represent the sign of the number. It would be kind of silly for us to pass the number and the sign to every single function that needed to use an int. Okay, the int data type kind of wraps all that information together into the type and makes it so the programmer doesn't have to actively think about all the component parts. In other words, we don't care how an int works, we just know what it does. Okay, and we humans do this all the time, so I don't really know how a car works, but I do know what a car is used for, and I know what operations I can use with it. I can turn the wheel, I can hit the gas pedal, I can hit the brake pedal, etc. Okay, so in C++, a struct allows us to group related data together. Struct is just short for the word structured. The data wrapped up in a struct can be of different types. So you might think an array is another way to group related data together. And it is, but one thing about arrays is all the elements of the array have to be the exact same type. With a struct, there's not that limitation. So a record or a structure is a group of related data associated with a single logical item. That's another difference between an array. Array is usually a group of data representing a collection of things, whereas a single object represents a single logical thing. Okay, you can think of a record or a struct as a single row in a spreadsheet. Okay? And each column as representing a different attribute of that item. So pretend we had a spreadsheet here. Okay? Well, every single row in this spreadsheet represents a single, let's say, student. Right? So every student has a name, a grade for assignment 1, a grade for assignment 2, and a grade for the final exam. Each row represents a single logical unit. Now each column, so here assignment 1, these are all the grades or all the attributes for a single student entity. So every student has a name, every student has assignment 1, assignment 2, and a final exam grade. Okay, so what we can do, we can create a new data type representing a student, and we would do that with a C++ struct. Okay, and this is the syntax. Struct is a keyword, and this basically says we're defining a new type called student. So this is not a built-in type, this is a type that we, the programmer, have decided to make. Then we have the set of curly braces, and inside we have all of the data members. Okay, so each data member must have its own type. Notice the ending At the ending curly brace, we have a semicolon. That is required. And remember, this is just the declaration of a type. The declaration of this type should always be at the top of the file outside of main. Remember, types are used to create variables. However, no variables have been created with this new type yet. Okay, no memory has been set aside. This is just the template that tells the compiler what a student variable would look like if we created one. Okay. So when we want an actual variable of this type, we're going to declare the variable just like we do any other variable. So let's look at this little snippet here. So if we wanted a variable called x, when the flow of control got here, this basically carves out room for an integer in memory, and we give that group of bytes the name x. Okay. Turns out it works exactly the same with the structured data types. When we want a student variable, okay, we give the type, which we've defined up above, and we give a name. Okay. So here we've declared this variable called s1. Then on the next line we declare another variable called s2. Okay. So we can go to memory. Let's imagine this is our memory here. And we now have these two variables called s1 and s2. Well, what does s1 look like? Well, it has a little bit of data allocated for each one of the data members. So we have a name, assignment 1, assignment 2, and final. Then we have another variable called s2. It has its own copy of those 4 data members: name, assignment 1, assignment 2, and final. These are totally distinct pieces of data. Okay. Each variable has its own copy of the data members that make up a student. Okay, a struct then is a lot like a cookie cutter, and our computer's memory is like the cookie dough. Okay, we use the struct to stamp out variables in memory. Okay, notice the syntax for creating student variables. The programmer specifies the data type, student, an identifier, and then a semicolon. And that's just like with any other variable type. That's how we created the int. We gave a data type, an identifier, and a semicolon. We do this exact same thing here with students. So type, ID, semicolon. When we create variables from a programmer-defined type, not a built-in type, we call these variables objects. And I'm going to start using the word objects quite a bit from now on. If you continue to learn more about programming, we're going to talk about object-oriented programming. And this is a style of programming where the emphasis is on creating new data types, just like I've done here with the student data type. The style of programming we've been doing so far is called procedural programming, where we focus on writing functions. So object-oriented programming is an extension of procedural programming. So it's good that we are learning the procedural style first and not putting the cart before the horse. And for a long time, decades, people only wrote procedural programs. It wasn't until about the early 90s or so this object-oriented programming really took off. Okay, so we have the objects in memory. S1 and S2 are the objects. You might be wondering, well, how do we access the individual data members in each one of these objects? Well, to do that, we use something called dot notation. Okay, so let's look at this line right here. This says s1 dot name. What that means is go find the object in memory called s1 and then look for a data member called name. And in this case, we're going to assign the value mark to that chunk of data. Okay, so here's the variable s1. Then we look for a data member called name. Okay, we found one here. Okay, and we're going to assign the value mark to that data member. Okay, then we say s1.assign1 is 87, s1.assign2 is 94, s1.final is 77. So 87, 94, 77. Okay. Next on this line, this says s2.name. This says go find the thing in memory called s2, and pull out the name data member and store LoRa inside there. Okay, so go find s2, look for the name data member, and we're going to store LoRa there. Then s2.assign1, if we set that equal to 91, s2.assign2, 98, and s2.final, 100. Okay. Okay, so that's the basic of how a structure works. I really like to think of the cookie cutter and cookie comparison. So the struct is the cookie cutter, the objects are the cookies, and our memory is the dough. We always take our structs and we stamp out these objects. Okay, so let's talk about some things we can do with structs. One thing we can't do is just do a plain cin to this variable called s1. So we cannot do this. However, we can do this. So it'd be nice if we could do this, I guess, but the computer has no real idea, which data member to assign which value. So here we really do have to separate it into 4 separate things, 4 separate cin statements. And then we're just very specific about which data members we're going to assign. Okay, turns out we cannot do any sort of arithmetic with our objects like this. We can't do this because not all the data members are numeric. And even if they were, however, the syntax of C++ says we can't do this. However, we can do this. We can kind of manually assign the numeric data members as the sum of other things. Okay, notice here I didn't touch the name because the name is not a numeric type. It doesn't make sense to do any arithmetic with that. We cannot do any sort of comparison with objects. Might be nice if we had a member-by-member comparison, but sadly we can't do this. Instead, we have to, again, kind of do it manually. We could say is S1's assignment 1 equal to S2's assignment 1, and is S1's assignment 2 equal to S2's assignment 2, and is S1's final equal to S2's final. Okay. One of the few things we can do, one of the few aggregate operations we can do, is we can assign one variable to another. So here's my 2 objects, S1 and S2. I fill all the data members for S1, and then down here we have an assignment statement. This is always right to left. And this basically says take all the data members that are in S1 and make a copy of those data members in S2. Okay, so again, this would be kind of like just copying member by member from S1 to S2. Okay, you can pass an object to a function. You can and should. So here's a little program that declares our student struct, and then we have a function called printStudent. We definitely want the declaration of the struct to be above the function prototype. Okay, so when the compiler gets here, it needs to know what a student is, and the only way to do that is to make sure the declaration is up above. So what do we do inside here? Well, we create these objects S1 and S2. I left out the part where we fill the data members, but we might want to call a function and pass S1. So we talked about functions last time. The flow of control is going to jump down to the printStudent function and we're going to pass into the function this variable s1. So s is going to be the parameter. S1, remember, this is called the argument. Okay. And what we're doing here is we're passing by value. Okay, and what that means is that a copy of the argument is made. That copy is called s. It's used inside the function, and then as soon as we're done with the function, s goes away. Okay, so the actual print student function just prints out the name and the values for the assignments. Okay. Let's look at memory when we call this function. Okay, so in main we've declared two objects, s1 and s2. When the flow of control gets here and we're calling print student, we want to pass in s1. So all the data members that are inside s1, they need to be copied into this thing called s. Okay. So when that function is called, we temporarily create this object called s, and we copy all the data members from s1 into s. Okay, so there's 4 data members. And then inside that function, right, remember the scope of the function, s is accessible for basically the entire function. S holds a copy of the argument. So when we say s.name or s.assign1, assign2, or final, we're really talking about that copy called s. And then whenever we get to the ending curly brace, remember what happens. The variable s goes away. So it's kind of ripped out of memory, and the flow of control returns back to main. Okay. And look what we do on the very next line. We call print student again. This time we pass in s2 as an argument. Okay. So what's going to happen? Well, again, somewhere in memory, we're going to make room for this parameter called s. It may land here, may land anywhere else inside here. Right? And what's going to happen, because s2 is the argument, we're going to copy all the values from s2 into s. The flow of control is going to jump into the function, and then when we refer to s, we're really talking about the copy of s2. When we come to that ending curly brace, the parameters, remember, go away, so they're ripped out of memory, and the flow of control returns back to main. Okay. And we have successfully printed out s1 and s2. Okay, so passing by value, remember, means making a copy of the piece of data. And it takes a certain amount of space in memory for the copy and a certain amount of time to copy the bits that make up the data. Turns out you can also pass by reference. So here's a very similar program, almost identical, with just the exception here that we're going to pass the student object by reference. Okay, remember, we get passed by reference by adding that ampersand next to the data type. Okay, so now what happens, again, we call print student with s1 and s2. Well, the first time we call print student, because we're passing by reference, s is just another name for this chunk of memory. And then the flow of control jumps to the function, and anytime we refer to s, we're really talking about, this piece of data. And then when we're done with that function, s goes away, the name goes away, the alias goes away, the flow of control returns back to main, and then we call the function again, this time with s2. Okay. And now s is just an alias for this chunk of memory. So before we had copies over here in memory. Now that we're passing by reference, we're just making aliases. So in the second function call, any reference to s is really referring to this object s2. Passing by reference saves us the memory it costs to hold the copy and all the processing time it takes to copy the bits over into the copy. And with large structures, you almost always want to pass by reference. So here's maybe a struct that represents an MP3 file. It has a title, an artist, a year, and then the actual music, right? That might be stored in this big array of bytes, so maybe 10 million bytes here. So that's definitely that's a really big piece of data, and we'd want to take advantage of how fast and memory efficient it is to create an alias rather than a full copy. Turns out we can also have these things called hierarchical structures. So a struct can have other structs, okay, or objects as data members, and this creates a hierarchy or nested structure. So let me give you an example of that. So here we start with a struct called name. A name is a string for the first, a character for the middle initial, and a string for the last. Now in our student struct, one of the data members is going to be this object of type name. So student now has a name and then 3 floats for the grades. To access the more complex data members, we extend our dot notation. Okay, so here's the full program where here we declare S1, and now we can say S1.studentName, that's the data member called student name. Well, it happens to be an object itself, right? Its type is name, and every name object has a first, middle initial, and last data member. So we can say S1.studentName.first, S1.studentName.middle initial, S1.studentName.last, S1.assign1. Again, that's just the plain old data member associated with the student object. Okay, so there's no limit to how much nesting you can do of these structures. You can have structure inside a structure inside a structure. Turns out we can also have arrays of objects. Okay, so this declares an array of 100 student objects, okay, where the student is this complex type. Now we can have a group of 100 of them. And if we were to look in memory, looks like any other array. Okay, so there's this name students that always refers to the very first element. Since there's 100 of them, the last one is going to have an index of 99. So from 0 to 99 are the indexes for the 100 students. Each one of these boxes, of course, has those 4 data members for the name, assignment 1, assignment 2, and the final. So I drew them kind of small, but each one of these is a full student with the 4 data members. To access the elements in the array, we use square bracket and dot notation. Okay, so when we say students at position 0, that's going to give us a student object. Okay. Once we have a student object, we can use our dot notation. So the dot assign 1 selects the data member for assignment 1. And what we can do is assign the value 78 to this student object's assignment 1. Okay, this is really powerful because now we can process an entire class of students inside of a loop. Okay, so if we wanted to print out all the student name, or all of the student information, not just the name, but the values for the grades, we can set up this nice simple loop from 0 to 99, and basically we're just accessing each one of the individual student objects. So I starts at 0, it goes up to 99, okay, and we're going to pull out the first, middle, and last name, then we're going to print the grades, assignment 1, assignment 2, and final. Okay, we could do it like that, or an even better solution would be to use a function. Right, so now printing 100 students is just basically 2 lines of code where we have our for loop that goes from 0 to 99, and then we select an individual student object. So students at I, remember, is going to be a single student. Remember that print student function we had before, either whether it's passed by value or passed by reference, it was expecting a student object. Well, now we can do quite a bit of work here with just these 2 lines of code and the 6 or 7 lines in the print student function. Okay, and that's a structured data type. And again, this is really important. We're going to do more and more of this if you continue on learning about programming. this idea of creating our own data types, having the programmer create our own data types, is very important, and it's really the heart of object-oriented programming.